So, throughout this course, I will be teaching you different hypertrophy tips, tricks, and methods. Now, before we get into the application, you're going to need a basic foundation of knowledge to fully understand the principles you're going to be applying throughout this course. The most obvious and important question to be asking is, what is hypertrophy? Muscular hypertrophy means muscle growth. It is simply the development of a muscle's mass, its density, and its capacity. The said principle is one of the most important concepts in sports science. It stands for specific adaptation to imposed demand, which simply means when the body is placed under some form of stress, it starts to make adaptations. If you look at this comical meme, we have two penguins floating on a piece of ice in a large body of water. They are discussing how global warming has made it difficult for polar bears to get them. And of course, there's a polar bear that adapted by learning to kite surf. Your body has the ability to make specific adaptations relative to the form of stress. This adaptation response allows the body to get better at withstanding that specific form of stress in the future. Muscle atrophy is the opposite of hypertrophy. The muscle loses its size. We've all heard the term use it or lose it. If there is no demand or stress, there is little need for a large muscle. You can see in this image how inactivity can cause atrophy. And over time, with regular exercise, the atrophied leg in this image can return to normal. The adaptation is specific to the demand. So if we don't use a muscle, the adaptation is to shrink. If we use a muscle, the adaptation is to increase in size. The more demand we put on that muscle, the greater the hypertrophy. So what exactly makes a muscle bigger? When someone performs resistance training regularly, they may notice some muscle growth. The growth is due to an increase in water, nutrient storage, number of myofibrils, and connective tissues. Hypertrophy is often broken down into two types: myofibrillar hypertrophy, often called functional hypertrophy, increases the muscle size by increasing the actual size of the myofibrils. Whereas sarcohyplasmic hypertrophy increases muscle size by increasing the volume of sarcoplasmic fluid in the muscle cell. The sarcoplasmic fluid is what contains a lot of the hydration in terms of water and nutrients in the muscle cell to supply it with fuel when performing endurance training. Many people in the fitness industry refer to bodybuilders as an example of sarcoplasmic hypertrophy and often state that their muscles look more puffy, while weightlifters demonstrate more myofibrillar hypertrophy and their muscles have a much denser look. Let's explore sarcoplasmic hypertrophy and try to uncover why it doesn't yield the large puffy muscles that many people think it does. Sarcoplasmic hypertrophy is accomplished by the expansion of the sarcoplasm. This occurs via an increase in the volume of the non-contractile sarcoplasmic fluid within the cell. And this cellular expansion allows for a greater storage capacity. In this diagram, we see a muscle, and from there we zoom in on an individual muscle fiber. The white space represents the sarcoplasm, which is the area that expands during sarcoplasmic hypertrophy. One of the main factors in sarcoplasmic hypertrophy is glycogen storage and hydration. As we use glycogen in training, one of the adaptations that occurs is an increase in storage capacity. As our muscle glycogen storage increases, we also see an influx of a muscle's hydration status. This increase in muscle cell hydration occurs because glycogen is often accompanied by water. And per 1 gram of stored glycogen, we also store about 4 grams of water. A standard hypertrophy diet will contain 1 to 3 grams per pound of carbohydrates accompanied by another 5 grams per 2 working sets on workout days. So a 200-pound male with a decent amount of muscle could be consuming 400 grams of carbohydrates daily with an additional 150 grams of carbohydrates on workout days, totaling 550 grams of carbs. 550 grams of carbs would be accompanied by roughly 2,220 grams of water. This person could have, assuming he was depleted in glycogen to start, a total weight fluctuation of 2,750 grams, which is roughly 6 pounds. An increase in storage capacity can help athletes who compete in sports that are heavily glycogen dependent, like track and field, hockey players, soccer players, and martial artists. Most athletes that would take advantage of sarcoplasmic hypertrophy actually look nothing like bodybuilders. And this is because the sarcoplasmic fluid only accounts for roughly 20% of a muscle cell. So a 20% increase in muscle storage would only amount to roughly a 2% increase in overall muscle mass. Myofibril hypertrophy is the main source of increases in muscle size. Myofibril hypertrophy is accompanied via the growth of myofibrils inside each muscle fiber. The myofibrils are the actual motors of the muscle fiber and are made up of contractile proteins that make the muscle fiber contract. In this image, the myofibrils of the muscle fiber are represented by the large red dots. Myofibril hypertrophy is often referred to as functional hypertrophy and is thought to be a compromise between size and strength, which is kind of a misrepresentation of what's actually occurring. By changing the workout variables, you are going to be accepting less muscle growth in exchange for an increase in strength. And this increase in strength actually occurs from an increase in motor unit recruitment. So which is better, sarcoplasmic hypertrophy or myofibrillar hypertrophy? See, here's where things start to get a little muddy. There are no examples of myofibrillar hypertrophy occurring without sarcoplasmic hypertrophy. And there are no examples of sarcoplasmic hypertrophy occurring without myofibrillar hypertrophy. Myofibrillar and sarcoplasmic hypertrophy have always been thought of as mutually exclusive, but we know that myofibrillar and sarcoplasmic hypertrophy never really occur without one another. So they are not mutually exclusive, but they could possibly occur consecutively, but at varying rates, meaning more overall myofibrillar hypertrophy than sarcoplasmic hypertrophy, or vice versa. A muscle cell is on average made up of roughly 80% myofibrillar proteins and 20% sarcoplasmic fluid. When myofibrillar hypertrophy occurs, the ratio stays the same and the entire muscle fiber increases in size. This is because an increase in contractile proteins also requires an increase in fuel. So if we want more working proteins, we need more stored energy to use them. From this information stems the million-dollar question: can sarcoplasmic hypertrophy occur at a faster rate than myofibrillar proteins can grow? Meaning, can we have more sarcoplasmic hypertrophy than myofibrillar? If this does occur, it would mean that the standard framework of a muscle cell could be adjusted from 80% myofibrillar and 20% sarcoplasmic to something different. Perhaps like 75-25, or in this example, a 70-30 difference, or maybe even a 60-40. In my opinion, however, sarcohyplasmic hypertrophy most likely won't occur at a faster rate than myofibrillar hyperproteins can grow because of how muscle fiber recruitment occurs while subjecting the muscle to metabolic stress. We will cover this more in depth in the mechanisms of hypertrophy module. Sarcohyplasmic hypertrophy, sometimes called non-functional hypertrophy, refers to gains in muscle size that are not associated with an improved force production. Whereas myofibrillar hypertrophy, often called functional hypertrophy, refers to gains in muscle size with the improvement of maximal force production. Many people often refer to sarcoplasmic hypertrophy as impractical and label it as all show, no go. Now, we've just learned that neither is mutually exclusive, so where does the increase in strength come from? As I said before, any increases in strength are from neuromuscular training zones. Simply by being in the lower rep range, your motor unit recruitment will get better and your strength will increase. Now, sarcoplasmic hypertrophy yields less force production, but can increase work capacity. So both should be labeled as functional, just relative to their application. This chart can help you to understand what's occurring between the two different types. Everything to the right of optimal hypertrophy training begins to increase capacity while compromising strength, while everything to the left begins to increase strength while compromising capacity. Hyperplasia is not hypertrophy, however, it does relate to how a muscle cell can grow. Hyperplasia simply means an increase in the number of muscle fibers. So the question being asked is whether muscle growth occurs primarily through hypertrophy, or can the number of muscle fibers increase via hyperplasia? The idea behind the hyperplasia would be if we could somehow increase the number of muscle fibers and then grow them as well, more total size could be attained. Studying hyperplasia is difficult because the research requires some way to count muscle fibers. The most common and successful method is the quail wing stretch, where they put a quail wing under a constant stretch 24 hours a day for 28 days with a progressively heavier load. The intense stretching and tearing of the muscle fibers causes hyperplasia to occur. However, this sort of research isn't really applicable with humans. Muscle satellite cells are a distinct lineage of myogenic cells that are responsible for mediating the postnatal growth and repair of adult skeletal muscle, simply meaning that satellite cells are a type of cell that are responsible for the growth and repair of adult muscle later in life. So when we exercise and cause muscle damage, satellite cells are activated to assist in the repairing of muscle fibers. And should hyperplasia occur, these satellite cells could be used to form new muscle fibers. So let's perform a quick review of the science of hypertrophy. The said principle stands for specific adaptation to imposed demands and determines how a muscle will respond to exercise. Its principles allow us to differentiate between strength training, myofibrillar hypertrophy, sarcohyplasmic hypertrophy, and endurance. Sarcohyplasmic hypertrophy is simply an increase in storage capacity via an increased volume of sarcoplasmic fluid. Myofibrillar hypertrophy is an increase in the actual myofibrillar proteins. Sarcohyplasmic and myofibrillar hypertrophy are not mutually exclusive and therefore are both always occurring. So when we talk about hypertrophy and an increase in muscle size, it's best to think of myofibrillar and sarcoplasmic hypertrophy as two pieces of the same puzzle. And any increases in strength or work capacity are related to the changes in the training parameters. And finally, hyperplasia simply means to increase the total number of muscle fibers.